Let's do a minimization example. Let's say we want to minimize c equals 5x1 plus 2x2 given these constraints and of course our non-negative constraints. So the first inequality would give me the boundary x1 plus 3x2 equal 15, and the intercepts would be at 0, 5 and 15, 0. So to graph that, I would have to plot this point here, and this is the point 0, 5, and then 15, 0 would be right here. Okay, so then I would, draw a line through those 2 points, and then I would test the origin, which is right here. And when I test the origin, I actually get a false statement. So that means I have to shade everything above this line. So I'm having trouble finding my mouse here. Okay, so if you would shade everything above that line. Now, and remember, we have to stay in the first quadrant, so we know we're not going to go left of the y-axis or below the x-axis. All right, now the other constraint, 2x1 plus x2 is greater than or equal to 20, its boundary would be 2x1 plus x2 equals 20, and it has intercepts. When x1 is 0, there's a typo there, that's 20, y is 20, and then when x2 is 0, x1 would be 10. I'm not sure, maybe I copied and pasted here. That should be 10, 0. Okay, so 0, 20, and 10, 0. Alright, so here's 0, 20, and this point right here is the point, let's see, I'll just go over here and do it. And that would be the point 10, 0. Okay, and then I would draw the line to connect those 2 points, 0, 20, and 10, 0. And then if I test the origin here, 0, 0, if I plug 0, 0 into this, I get 0 is greater than or equal to 20, which of course is a false statement. So therefore, I would shade above this line. So I would shade everything out here. Let's see if I can get a little closer. There we go. So I would shade everything on this side of that line. Now, if you shade everything on the outside or above both lines, then the region you're going to get is this dark green region. But remember, this dark green region is bounded by the y-axis here. So it's bounded here by the y-axis, and then it's also bounded by the x-axis down here. So you're bounded here by the x-axis, and you're bounded, let's see if I can get that to go straight. All right, so you're bounded here, and then it takes a turn here at 0, 20, and then it comes down here, and where it intersects that other line, that's actually the point 9, 2. I'll talk about that in a minute. And then it takes a turn right here, and it hits the x-axis, and then it takes a turn in this direction. So basically you have 1, 2, 3 corner points, 0, 20, 9, 2, and 15, 0. Now again, to get the 9, 2, you just want to know where the lines intersect. So basically all you have to do is solve this system, and it'll tell you where those 2 lines intersect, which should give you 9, 2. Now, this region is unbounded, so a minimum exists, but no maximum. Now, the objective function was 5x1 plus 2x2, and my 3 corner points were 0, 20, 9, 2, and 15, 0. Now, if I plug 0, 20 in, I get 40. If I plug 9, 2 in, I get 49. If If I plug 15, 0 in, I get 75. Now, since I want to minimize this, and it's a bounded region, I know it has a minimum, and the minimum would be the smaller of these three values, which would actually be 40, and that occurs at the point 0, 20. Now again, I'm warning you again that the optimal solution is not always the point inside the region. You know, it can be the point on one of the axes. Okay, so let's change the objective function. So let's make it, instead of 5x1 plus 2x2, let's make it 5x1 plus 20x2, and let's see what happens if we use those same corner points. Well, if we plug 0, 20 in, we're going to get 400. If we plug 9, 2 in, we're going to get 85. And if we plug 15, 0 in, we're going to get 75. So by changing that coefficient, it actually changes the minimum. So now the minimum would be 75. Actually, those should say C, not P, but the minimum would be 75. And so it would be 75 at x equal 15 and y equals 0. Okay, now neither one of these would actually have a maximum because it's an unbounded region. Okay, there's a couple of practice problems there that you can practice on. I noticed here I have z here and p here. Either change all these to z or change the original function to p. So I need to fix that. So change all of those to z, because whatever the objective function is, that's what that variable should be. In this case, I use z. So anyway, there's a couple of practice problems that you can do on your own there. Okay, now let's go ahead and take a look at another one. We actually did this one earlier, so I'm not going to spend a lot of time on the graphing. But notice I asked you to both maximize and minimize this one. And this region we graphed earlier, and so in a previous video you'll see that what we get is we get this triangular region right here that's bounded below, right in here from 5, 0 to 7, 0, and then it's bounded along this piece until you get up here to the point 3, 4. And so it's that triangular region here bounded by 3, 4, 5, 0, and 7, 0. So those are your three corner points. And the function was 3x1 plus 4x2. Now since this is a bounded region, remember if I can draw a circle around it, it's a bounded region. So since it's a bounded region, it has both a maximum and a minimum. So let's plug in the three corner points and see which one's the smallest and which one's the biggest value for z. If I plug 5, 0 in, I get 15. If I plug 3, 4 in to this, I get 25. And if I plug 7, 0 in, I get 21. So we actually have a maximum of 25 at the point 3, 4, and we have a minimum of z equals 15 at the point 5, 0. Now here's another couple of practice problems that you can try and see. One thing about this problem is interesting. Remember I told you you could only have one minimum, but it could occur at two different points. So when you work this one, you'll actually find that you actually get you only get a minimum of 160, but it occurs at either 4, 6 or 16, 0. If that happens, then you can just pick whichever one you want. In the practical sense, you should list both as answers, but in the practical sense, if you're trying to decide whether to manufacture 4 of one kind and 6 of the other, or 16 of one kind and 0 of the other, then you would have to figure out which would be better in your case. Okay, this is the medicine problem. I set it up earlier. So I set up the constraints in an earlier problem. So we already know how to graph this. Well, maybe we didn't graph it, but what I want to do is I want to minimize this function 3x plus y. And so I'm calling it W for the just for the amount of drug. You could use any letter you wanted to instead of W, but I'm not sure why I used W. But W is 3x plus y. Now, I'm just going to kind of gloss over the graphing part. If you graph this region, then basically you're going to get a region that's, of course, bounded here by the y-axis, and then it's going to be bounded here at the point 0, 42, and it's going to turn, and then it's going to hit this point 422 where the two lines intersect, and then it's going to turn again and come down here, and then this point's going to be 15, 0, and then it's going to go along the x-axis. So that blue region is the feasible region, and you have 3 corner points, 0, 42, 422, and 15, 0. And so if you plug those corner points into the objective function, again, that's an unbounded region, 3 times 0 plus 42 is 42, 3 times 4 plus 22 is 34, and then 3 times 15 plus 0 is 45. So it only has a minimum, and of these three values, 34 is the smallest, so the minimum is z equals 34 at the point 422. So you should administer 4 units of drug M and 22 units of drug N to minimize drug W and satisfy the constraints. So you might want to read the problem before you go through this, because I didn't read it to you. On these last two problems, I just want you to focus on setting them up and read them first. Pause the video and read them. But what you're going to find out on this problem is we want to minimize cost, and cost is $2 times x1 plus $1.25 times x2, and you've got to have the minimum daily requirements of 900 units of vitamin, 2200 units of protein, and 800 units of carbohydrates. And so if you read the problem, you'll see that you get 300 units per each unit of x1 and 100 units of vitamins per each unit of x2. So that's your total vitamins, and that has to be greater than or equal to 900. And then for protein, you get 400 units for each unit of x1 and 300 units for each unit of x2, and then it has to be greater than or equal to 2200 units available for protein. And then for carbohydrates, you get 100 units for each x1 and 200 units for each unit of x2, and those have to add up to be greater than or equal to 800 for the carbohydrates. And then, of course, x1 and x2 have to be non-negative. So then you can graph this, and you can just do this by practicing it. And these are your 4 corner points. And then if you plug each of those corner points into the objective function, you'll see that you actually get a minimum of, let's see, we get a minimum of $8.50 at the point 42. So that would be your solution there. And go ahead and read number 3 and see how I set this one up, and look at the difference between number 2 and number 3, because this will come up later. Number 3 is a maximization problem, but all the problem constraints are less than or equal to, but they're less than. This is actually called a standard maximization problem, and we're going to learn how to solve it using the simplex method. This problem up here, you're actually minimizing, and all your constraints are of the greater than or equal to form, and that's called a standard minimization problem, and we can solve this problem using the dual method. So we're going to have to get away from this graphing method, because I told you earlier we can't solve every problem by graphing, because sometimes we just have too many variables or too many constraints. So in the next section, I'm going to teach you how to solve by another method.